Okay, good morning, good afternoon, good evening from wherever you are. Sorry for that slight delay in getting us started. We have today with us Professor George Hirasaki, who's going to give a talk on how foam develops apparent viscosity during CO2 enhanced oil recovery. Welcome to today's Geoscience and Geoenergy webinar. If you're missing Hardy, he is driving he's on his way home, so he's going to join us in a few moments. It is both Hardy's and my great honor and pleasure to introduce Professor Hirasaki, who joined the Rice faculty after 26 years with Shell Development and Shell Oil Company. His research in fluid transport through porous media ranged from microscopic scale intermolecular forces governing wettability to the megascopic scale numerical reservoir simulation for field-wide modeling. A recurring theme of Professor Hirasaki's research is the dominance of interface and the determination of fluid transport processes. Fluid flow through rocks and soil in pore space that are on the order of microns. The relative transport of phases and components are governed by the degree of wetting of the solid and the fluid phases and the absorption of species on the fluid and solid surfaces, in addition to the usual transport coefficients such as viscosity and diffusivity. It is really a great honor and pleasure to have George speaking with us today. Thank you all for joining. As every week, please enter your questions into the chat during and after George's talk. One of your questions may be triggering a question or comment from one of the other audience members. And without further ado, I'm very happy to give the floor to George. And George, it's all to you now. Please do start your presentation.
Thank you, Sebastian and Adi. I appreciate the invitation, and I apologize that it has to be by Zoom rather than in person. I'm somewhat handicapped in Zoom presentations because I can't see my audience, and I don't know your responses, but let's see if we can make this work out the best as we can. So the title of the presentation is How Foam Develops Apparent Viscosity in CO2 Enhanced Oil Recovery. This is the outline of the presentation. I'll first start talking about the current state of the art, choice of surfactants, the results in smooth capillaries, effective constrictions, what we mean by foam texture, mechanisms of foam generation, and mechanisms for foam destructions. Then we'll talk about the population balance that has to do with the accumulation, the balance of foam generation and destruction as well as convection. Then we'll discuss the minimum pressure gradient for foam generation, empirical foam models for reservoir simulation, and experiments and simulations for field applications. And then we'll have the conclusions. So let's talk about the current state of the art. We'll talk about both measurements and modeling. And what we'll be talking about is apparent viscosity. Now, apparent viscosity is given by this equation. It's just a restatement of Darcy's law. The apparent viscosity is proportional to the pressure gradient multiplied by permeability divided by the flux of water and gas. This is just taking Darcy's law and treating the water and gas as a combined fluid, and the apparent viscosity is the apparent viscosity of the foam. And this will be used in a reservoir simulator. So now let's see what the apparent viscosity looks like. And so we have apparent viscosity on this scale from 0 to 400 centipoise. And on this scale, we have the foam quality. The foam quality is the gas fractional flow. That is the gas flux divided by the water plus gas flux. Or we just call it fractional flow or foam quality. We have results of several different permeability porous media from 551 millidarcy, 170 millidarcy, 57 millidarcy, and 33 millidarcy. Over an order of magnitude change in permeability, we see a change in apparent viscosity. What's common in all of these is that we see as we increase the foam quality, the apparent viscosity increases. It goes through a maximum and it decreases as we get drier. We refer to this quality where it reaches the peak as a transition foam quality. And this is sometimes referred to as the wet foam regime. This is the dry foam regime. The matter of first importance in working with foam is the choice of surfactant. And the choice depends on the reservoir. Is it sandstone or carbonate? Sandstones generally have a negative surface charge on the mineral surfaces, while carbonates generally has a positive surface charge on the mineral surfaces. This is very important in the absorption of surfactant. Salinity is an important variable, not just the salinity, total salinity, but the hardness as well, and temperature. The type of surfactants. First, let's just talk about the different types of surfactants: anionic, non-ionic, cationic, and zwitterionic. Examples of anionic surfactants are sulfonate, sulfate, ethoxysulfate, and ethoxycarboxylate. Now, what I have not included is what I think would be my favorite surfactant if it wasn't for the cost of it. This would be ethoxylated sulfonate. These are temperature resistant to stable at high temperature and high salinity and high hardness, but it's very expensive, is not economical for enhanced oil recovery. Non-ionic surfactants. The most common non-ionic is the ethoxylated alcohol, but more recently we have the glucoside, which is a sugar-based surfactant. Cationic surfactants, we'll talk about amines and diamines. And zwitterionic surfactants are surfactants that have both an anionic and a cationic charge on the molecule so that the charges are balanced. And then the result of the charges being balanced, it's less sensitive to salinity. The examples are betaine, amidobetaine, and sulfobetaine. Another important factor is the carbon number of surfactants, generally from 12 carbon to 18 carbon. 12 carbon is just about the minimum number of carbon that you need on the surfactants to be considered as a foamer. That if it's less than that, foam is not very stable. As you increase the carbon number, generally the foam will become more stable until you reach some limiting factor. And the factor could be surfactant precipitating, surfactant absorption on the formation, or it could be partitioning into the oil, having unfavorable phase behavior, destabilizing the foam. Important consideration in the choice of surfactant is low absorption of formation minerals. This is the reason why it matters where the formation is sandstone or carbonate. And then depending on if it's sandstone, you would generally use an anionic surfactant. If it's a carbonate, you may use a non-ionic surfactant or cationic surfactants. Now, cationic surfactants are more expensive, and so you may choose to use the non-ionic surfactant if the temperature is low enough. If the temperature is high, you may have to either use a glucoside or a cationic. And you need to have low absorption. One issue with the zwitterionics is that the zwitterionics is favorable in that it has very little sensitivity to salinity, but it tends to have a very high absorption on formations. The very important in the selection of surfactant is the chemical stability. And then there's two kinds of, well, it should be chemical stability and physical stability. Let's first talk about physical stability. The non-ionic surfactant ethoxylated alcohol, it's known that more like ambient and moderate temperatures, it works well. But there's a certain temperature that ethoxylated alcohol has what is called as a cloud point temperature, and where the surfactant will start precipitating or going into a viscous liquid phase, and this is referred to as a cloud point. And then if it just the viscous liquid phase, it would be surfactant rich phase. In the presence of oil, the surfactant will partition to the oil, and this referred to as a phase inversion temperature. So that's the limitation of ethoxylated alcohol at higher temperature. Let's talk about chemical stability. Sulfonates is much more stable than sulfates when it comes to elevated temperature. At elevated temperatures, sulfates tend to hydrolyze into the alcohol, losing the sulfate group. And this hydrolysis rate is a function of the pH. If you add CO2 to the system, lower the pH, the hydrolysis rate is much faster than it is at neutral pH. And the chemical stability is also important in the zwitterionics. Betaine we found to be stable at elevated temperature regardless of the pH. Aminobetaine we found to be stable at pH 7 elevated temperature, but if you had acidic or alkaline pH, it tends to degrade at elevated temperature. So now let's go back to the question of how does foam gain flow resistance? We'll look at smooth capillaries as the simplest case and look at the contributors to flow resistance. First of all, whenever we have flow in a smooth capillary, we may have slugs of liquid, and the liquid, of course, has a viscosity, and then it'll contribute to the resistance. But whenever you have just a single bubble in a capillary, there'll be interfacial deformation as a result of the flow. This is described by Bretherton in the 1960s. As a result of the flow, the liquid will be entrained by the moving bubble, and then you'll deposit a film whose thickness is proportional to the, I think, the 2/3 power of the capillary number. And then on the back of the bubble, because the capillary suction will tend to draw the liquid out of the film back into the bulk, and this results in a thinning of the film at the back of the bubble. The result of this film thinning is, look at the difference in the radius of curvature of the back of the bubble compared to the front of the bubble. The difference in the radius of curvature results in the difference in pressure drop across the interface. And this pressure drop across the interface gives you resistance to flow. And then you can calculate the analytical solution for the apparent viscosity as a result of just bubbles flowing in a capillary. Another factor is the surface tension gradient. When we have foam, we have surfactant solutions. Surfactant absorbs at the gas-water interface, and then if you have a bubble that's traveling in this direction, there are two stagnation points, the front stagnation point and the back stagnation point. At the front stagnation point, the surfactant is being swept away. On the back stagnation point, the surfactant is accumulating. And so you have a higher surfactant concentration at the back of the bubble than you do in the front of the bubble. Thus, there's a surface tension gradient along the bubble. This results in additional resistance. So again, in smooth capillary, let's look at the apparent viscosities of bubbles in smooth capillary. This apparent viscosity is related to Poiseuille's law. And so we have the apparent viscosity as a function of the bubble velocity. So without a surface tension gradient, this is the behavior that you have based on the Bretherton theory. The apparent viscosity has a slope of minus minus 2/3. Now, if you have surface tension gradient, these are the measured points. Notice that the apparent viscosity is an order of magnitude greater as a result of the surface tension gradients, but it still seems to have the similar power law behavior. Now let's look at the effect of bubble size. And so on this plot, we have the apparent viscosity as a function of the bubble radius divided by the capillary radius. So small bubble radius, we have bulk foam. Larger bubble radius, we have lamella moving in a capillary. But notice the slope of this curve is -2. And so it's the apparent viscosity goes from 1,000 centipoise to 1/10 of a centipoise, only over 2 orders of magnitude of the ratio of bubble size to radius. And so it's the ratio of the bubble size to the capillary radius that's an important factor in the apparent viscosity. What happened to the, I need to advance the slide. Okay, here we go. Now let's look at the effect of constrictions. Suppose we have a constricted capillary shown like right here. If there's no pressure gradient, then a lamella would just reside at the constriction in the capillary. If you were to apply a pressure gradient, then the lamella will bulge out and it will be pushed into the pore body. Now, once it traverses the pore body and approaches the next pore throat, it will spontaneously jump into the next pore throat. There's no recovery in energy in the spontaneous jump, but you have to exert energy to move the lamella out of the pore throat. So this results in an additional restriction. And so this is the apparent viscosity as a function of the gas phase velocity in a bead pack. This is a theory for if you had just smooth capillaries, and then this is the experimental data whenever you have a single train of bubbles in a bead pack. You can see that the apparent viscosity is more shear thinning than it was for just bubbles in a smooth capillary. And it's the approaches that a smooth capillary at the higher velocity, but it becomes much greater at the lower velocity and more than an order of magnitude greater. Why I'm trying to advance my slide. Why does my slide? Okay, let's. My slide isn't advancing. What's happening? Okay, here we go. Now let's look at foam texture. We can have either continuous gas foam or discontinuous gas foam. When we have continuous gas foam, we'll have some regions of stationary bubbles, but then you may have a continuous gas channel. Continuous gas channel, gas has a very low viscosity, very little resistance, and is a Newtonian fluid. This is generally what happens when we have a weak foam. When we have a discontinuous gas foam, the only way the gas can move is by moving the lamella. And then the lamella gives you resistance to flow like I described earlier. And so if it's a coarse textured foam, you have only so many lamella per unit length. You have a certain pressure gradient. If it's finely textured foam, you have more lamella per unit length. You'll have much more resistance to flow. Let's examine the mechanism for foam generation. We'll look at bubble or lamella division. Well, we already looked at capillary snap-off, but there's a lamella division. Branch points in flowing train of bubbles offer opportunity for bubble or lamella division. And this is responsible for the transition from continuous gas foam to discontinuous gas foam. So let's look at what happens at low pressure gradient. At a low pressure gradient, let's suppose that you have a train of bubbles moving, let's say, along this path, but this branch, the bubbles are stationary. In that case, if you have continuous gas, well, continuous gas is just a flow. If you have foam bubbles, the bubbles will just pass through, not change in size. But now let's suppose that you increase the pressure gradient enough such that the bubbles in this branch starts moving. And if that's the case, a bubble that's approaching a branch point, if the bubble is big enough, that bubble becomes two different bubbles, and then you divide a bubble into two smaller bubbles. And of course, this will continue only until the bubbles become similar to the size of the pore, and then you won't get any further division. Now let's look at the mechanism for foam generation by capillary snap-off. The mechanisms for capillary snap-off are pore body, pore throat, contrast, and water saturation. Or it could be on a more macroscopic level, a permeability, contrast, and water saturation. What you have is a spontaneous migration of water from the larger to smaller pores. The capillary pressure for snap-off is 1/2 when it's less than 1/2 of the capillary entry pressure. So let's look at what happens in a constricted capillary. Suppose that you have a constricted capillary that's wetted by a surfactant solution. What you'll notice as a function of time, because of capillarity, the liquid film in the constricted portion of the capillary, the water accumulates, gets thicker, and then we get snap off, and then a liquid bridge forms. And then if there's flow, the liquid gets expelled, it forms a lamella in the larger capillary, and then it repeats itself. And this is the most fundamental level of what we mean by capillary snap-off. Okay, now let's look at what happens in porous media. We'll demonstrate an experiment as well as a numerical simulation population balance of what happens in a heterogeneous system. So we have a bead pack with a region of low permeability, high permeability before, and high permeability after the low permeability region. And we introduce the liquid and the gas separately so we don't generate foam as a result of the inlet conditions. And then on the at the outflow end, we withdraw the liquid and the gas separately so we don't generate foam as a result of capillary end effect at the outlet of the bead pack. And we can measure the pressure drop across this section by having pressure taps. We'll see simulation results describing what's happening inside this system. And so let's talk about mechanism for foam destruction. The capillary pressure exceeds maximum stable disjoining pressure. The lamella will collapse. And this limits the bubble refinement, because whenever your bubble gets smaller, you get more resistance to gas flow, and then that drives down the water saturation. That increases the capillary pressure, and then when the capillary pressure gets large enough, the foam starts destabilizing by coalescence. Another mechanism for foam destruction is mass transfer from small bubbles to large bubbles. Smaller bubbles have a higher pressure than gas bubbles, and if the small bubble is next to a larger bubble, the difference in pressure results in difference in solubility in the water, and then the water has to the gas can diffuse between the small bubble to the larger bubble through the thin film. This is referred to as Oswald ripening. Another mechanism for foam destruction is spreading of oil at the gas-water interface. That's why the oil can destabilize, but it depends on the spreading coefficient or the degree of spreading. Let's look at a population balance of bubble sizes. and I'm going to simplify it a little bit. And what I have in gray that I'm not going to show an example. So in a population balance, we have flowing and stationary gas bubbles. Now, I'm not going to include the stationary gas bubbles. And the population balance, we have size distribution. I'm going to just work on the mean size of the bubble. The bubble density is a dependent variable. That is the number of bubbles per unit volume of gas. In the population balance, we have the accumulation of bubble density is equal to minus divergence of flux plus the generation rate minus the destruction rate. I'm not going to show the destruction rate in the example. We also have the mass balance for two-phase flow. That is just a Buckley-Leverett expression for gas-water flow. So this is our population balance simulation where we have generation only by snap-off. And we have profiles as a function of dimensionless distance, 0 to 1. This would be the inlet, this would be the outlet. The permeability would be high permeability in the first section, region of low permeability, and region of high permeability. And then this scale will be between 0 and 1. The water saturation given in the solid curve is shown here. In the high permeability, it's something greater than 40%, and then it dips a little bit before going into the low permeability. Then it's right about 40%, and then we see an increase in saturation before going into high permeability, and then it drops to a much lower saturation. The dash curve is the calculated capillary pressure. It's low in the high permeability, it gets higher in the low permeability, and it gets medium value in the high permeability. The dotted line is the critical capillary pressure for snap off. And so it's if you get below this capillary pressure, you'll have snap off. If above it, snap off, what doesn't occur. And so that's the critical capillary pressure. This is the critical capillary pressure. And so in red, where the capillary pressure is less than the critical capillary pressure, you're having foam generation here and then near the outlet of the low permeability region. This dotted curve is a bubble size scale by factor of 20. And then you can see in the high permeability region, the bubble size is infinity. And then as you go from high perm to low perm, it plunges down very rapidly to some value. Then it plateaus. Then as it approaches near the outflow end, then it starts dropping again because you're generating foam again. And so this rapid drop in bubble size was due to the generation as it entered the lower permeability. And then this again drop in bubble size as a generation by snap off as it's leaving the low permeability to the high permeability. And then once it gets in the high permeability, there's no change in the bubble size. So this is at a gas fractional flow of 0.9. Let's go to gas fractional flow of 0.99 or 90%, 99% quality. Everything is qualitatively similar, except now the capillary pressure in the low permeability is greater than that of the critical for snap off. And so you don't get below the capillary pressure for snap off until you go at the transition from the low permeability to the high permeability. And so the region in red is where the capillary pressure is less than the critical capillary pressure for snap off. And then no longer as you get to high permeability. And so the dotted curve is a bubble size. It goes from infinity to starts dropping once you start generating foam. And then once you exit the low permeability, get in high permeability, there's no longer any foam generation, so the bubble size stays the same. Those were the simulations. Now let's look at the experiments that happened about more than a decade later. And so let's look at the heterogeneous column and the homogeneous column. Heterogeneous column, we have a sandpack, inflow in, outflow in. The first section is 70 Darcy, next section is 16 Darcy, 70 Darcy, and 16 Darcy. The homogeneous column is just 9 Darcy uniformly. And then when we inject gas into the homogeneous column, then this is where we have gas after 0.3 pore volume, at which point we got gas breakthrough at the outflow in. And this is the pressure drop in PSI for the homogeneous gas bag. We can see just a very moderate pressure drop because with the homogeneous column, we just have continuous gas flowing across the top. But now let's look at what happens in the heterogeneous column. Okay, so point 1 right here that's the point whenever the gas filled the high permeability region hasn't yet entered the lower permeability region because of capillarity. Point 2, just a little while later, that's whenever the gas in the low permeability region went across and reached the interface of the higher permeability region. It didn't take long because it was just a continuous gas. Okay, now let's look at between point 2 and point 3. Point 3, first of all, it took a long time. And the second, notice that the pressure drop started to increase. 3 was whenever the gas front got to right here. What is happening as gas is leaving the low permeability to high perm, we're starting to generate a strong foam. The strong foam, being much less mobile than the water, is piston-like displacement. And so it takes a long time to get from here to here. And point 4 is that now we're going into from 70 Darcy to 16 Darcy, a lower permeability, and so the pressure gradient is increasing much more rapidly. And then 4 is when we finally get to breakthrough. So this is experiment, which is a description of what we were showing earlier in the population balance simulation. Here are some more recent experiments done at TU Delft. The minimum pressure gradient for foam generation. This is where the group in Delft did the experiments in a porous media. They had 3 sections. The first section 1 had a narrow cross section. Section 2 had a larger cross section. Section 3 had the largest cross section. And so as you flow through this system at a fractional flow of 88%, you have high velocity in the first section, intermediate velocity in the second section, and low velocity in the third section. And so at the time, whenever we had flowing through the system, look at the pressure gradient as a function of the total superficial velocity. And so looking up here, that the open squares represents section 1, that is in the narrow section where we had the high velocity, we have a large pressure gradient. And this is the middle section where we have lower velocity, we have a lower pressure gradient. And then in the black would be section 3 where the velocity is the lowest, the pressure gradient is even less. And then, so if you get slower than this, then the foam would collapse. But then if you were to now start increasing the flow rate, that whenever the pressure gradient gets above this critical pressure gradient for foam generation, then it'll jump back up to the strong foam region. And so this is what we refer to as the minimum pressure gradient for foam generation. And this is typical of what happens in homogeneous systems in the absence of capillary snap-off. Now let's go to the present time. I should make this 2023 because it's not yet in print, but has been accepted for publication. Here we have 1% AOS 1416 and 173 Darcy homogeneous sandpack with a constant gas flux. And then we'll be changing the water flux such as to change the foam quality from dry to wet. And we'll repeat the experiments with different multiples of the gas flow rate. The blue will be 1x, green will be 3x, yellow will be 9x, red will be 18x. And so we're going to do 18-fold change in the flow velocity. And then we'll measure the pressure gradient. And from the pressure gradient, you can calculate the apparent viscosity. And then we have a capillary probe so we can measure the capillary pressure inside the sandpack at the same time. So now let's look at the pressure gradient. Whenever we have the lowest gas rate and start increasing the liquid rate, and each of these points represents steady state results, the pressure gradient was increasing as we start increasing the amount of surfactant solution. Then it reaches a plateau and goes back down. This is at a 3 times higher flow rate, 9 times higher flow rate, and 18 times higher flow rate. Okay, if we were to calculate the apparent viscosity, like I described before, as a function of the foam quality, these are the results. So this is the result that you have at the lowest foam quality, lowest gas velocity. This is a 3 times higher gas velocity, 9 times higher gas velocity, 18 times higher gas velocity. And so at the lowest flow rate, you can see that we were bubble generation limited, and we had to exceed a cap. But if you were to increase the flow rate, then we generate foam by lamella division, and then we get something that's much more typical and like in consolidated rock, where you can have capillary snap off. Now let's look at the capillary pressure. This is a capillary pressure at the lowest flow rate, the intermediate flow rate, and then the 9x flow rate and 18x flow rate. And this is more of what we expected when we talked about limiting capillary pressure. And that's the case whenever the higher flow rate, we can generate foam by lamella division. But this, if we had capillary snap-off like in a heterogeneous rock or consolidated porous media, this may be more typical behavior. But when you have homogeneous system, you may be limited by foam generation, and we may get results that's more typical as what we see at the low flow rates. Now let's go to the empirical foam models for reservoir simulation. To bring us to the current time, we had the CMG STARBS foam model. This model was introduced by Bill Rawson before he came to TU Delft. He was still at University of Texas in the year 2000. And then this foam model was based on the concept of limiting capillary pressure, that as you get near a critical water saturation, there'll be a big change in the foam stability. And that model was used to develop the STARS model. So this model, the gas mobility is a function of the water saturation, the velocity or the capillary number, the surfactant concentration, and the oil saturation. And so here are some experimental results. These experiments were done at TU Delft and then published by our student that spent time at TU Delft, and then continued the interpretation and developing the method to fitting algorithm for fitting the experimental data to the curves. And then we have data, the blue is for nitrogen foam, methane foam and CO2 foam. And then the points are the experimental measurements. The curves are the fit for the STARS model using the parameter estimation strategy that Young Chao had developed. And so you can see that you can fit the experimental to you can fit the experimental model, data to the STARS model using the parameter estimation. Now you may be wondering, well, why is CO2 weaker than nitrogen foam? Well, CO2 is much more solubility in water than nitrogen. Now I mentioned to you that when you have a small bubble next to a larger bubble, the smaller bubble is a higher pressure than the larger bubble, but they may be just separated by a very thin lamella. And so CO2 being more soluble in the water, the mass transfer will be much faster with CO2 than nitrogen. So that's a simple explanation for why the difference between the different gases. Now let's look at experiments for fuel application. Our sponsor had very harsh conditions. We had to evaluate a foam system at a temperature 120 degrees Celsius, 3,400 psi CO2, and 22% TDS. And this is hard brine, not just sodium chloride brine. And it's a limestone formation. So this is very challenging. It's a carbonate formation. Then anionic surfactants would have very large absorption. And then ethoxylated alcohol, the temperature is too high. We couldn't use it. And so we used the anionic surfactant, TTM, which is a 16 to 18 carbon diamine. Diamine has two amine groups on the molecule. It's a cationic surfactant. So now let's look at its behavior in the laboratory. This is the apparent viscosity in centipoise, foam quality going from 0 to 1, or it's a fraction instead of a percent. And then results for 54 millidarcy and 321 millidarcy. This is apparent viscosity as a function of concentration. The experiments are shown by the symbols. The curves are fit to the experimental data for the STARS model. So this is a simulation for the field application. So we have a cross-sectional view with horizontal wells. The distance between injection wells and production wells is 500 feet. Thickness of the formation is 44 feet. We have horizontal wells, injection wells here and here, and then the horizontal production well is here. The permeabilities are shown by the different colors. The red intervals are 321 millidarcy. The blue intervals is 33 millidarcy. 2 orders of magnitude difference in permeability. So this is extreme case of heterogeneity. Now let's look at the simulations for field applications. Well, we just have CO2 and brine, no foam mobility control. And we have the cross-section at different times. The color code shows the oil saturation. Red is high oil saturation, green is low oil saturation. The first panel is after 1 year. The injection well is here and here. The lower injection well just injects CO2. The upper injection well is injecting CO2 and brine at the fractional flow is given somewhere. And then you can see that we're injecting here, but notice that the CO2 goes into the upper high permeability interval. After 2 years, the CO2 has gone all the way across to the production well. And after 5 years, it's starting to move in the lower higher permeability interval, but it's now you're producing a CO2 at your production well because it's going over the top at the high permeability interval and is coning down to your production well, even though it's a horizontal well. Okay, this is 1, 2, and 5 years. This is after 8, 10, and 15 years. Much larger time interval, but look how slow the CO2 front is moving. 15 years, you still have all of this unswept oil. This is without mobility control. Now let's see what happens when we have foam mobility control. This is exactly the same simulation, except instead of just brine, we have 1% TTM in the brine, and everything else is exactly the same. This is after 1 year, after 2 years, after 5 years. We can see that to 5 years, we can already see much more advance in the low permeability region because the pressure gradients are much higher. This is after 8 years, after 10 years, and 15 years. We're able to sweep the entire reservoir with the exception of just a little bit along the bottom. So in conclusion, the choice of surfactant is essential. The bubble size and distribution governs the foam viscosity. Bubble generation is governed by capillary heterogeneity and are exceeding minimum capillary pressure. Foam strength is limited by capillary pressure and mass transfer. Empirical models are available for fitting measurements and applying in simulators. Reservoir simulators are available to evaluate the benefits of foam mobility control for enhanced oil recovery. The final slides are the references that are used to show these slides. You can have the presentation and then look up these references if you want to follow it further. And so with that, I conclude the presentation and turn it over, question and answer. So Sebastian, I'll let you take it over from here.
Thank you very much, George, for this very interesting talk. We see a lot of questions. So this is the first time that Sebastian and I switch our roles. So he started the webinar. Now I'm taking the questions, and I'm delighted to do so. And we have some technical questions and some broader. I start with some technical questions to make the topic a bit more clear to the wider audience. We have a question from Christine Meyer. She's asking, after thanking you for the great talk that you just delivered, could you comment a bit on how fractures or high contrast flow channels would impact the foam generation and especially propagation and stability?
Well, when you have a fracture system, then foam can be very helpful. We have done some studies of that, but the generation of foam may be more challenging. We haven't studied generation of foam in fracture systems, but we may think of fracture systems instead of being a uniform fractures. It may be fractures are probably constricted. They may be plenty of opportunity for snap off, and then generally the pressure gradients are very high in fractures, and so we may have the pressure gradient high enough for generation by lamella division. And so it's quite possible that in practical fracture systems that we may have generation, if not by snap off, but by bubble division as a result of the high pressure gradients that we'll have in the fractures.
And following the same line, it's about the pressure gradient also, a global pressure gradient in the reservoir. So how would the distance between injector or producer or the impact of the entire global pressure gradient on the foam propagation and stability would be?
Yes, the pressure gradient is a very important limitation that you want to increase the pressure gradient in order to mobilize the unswept oil. This is the purpose of having foam for mobility control. Now, that in some cases you may be limited by the fracture gradient. You don't want to fracture the formation, and so if you exceed the fracture gradient, then you'll have loss of your injected fluids to some other interval. The Sonora pilot was a good example of that. They exceeded the fracture pressure by doing co-injection, and then it never performed well after that. And so that's where we learned it was very important to alternate surfactant and gas injection, and watch your make sure that you stay below the fracture pressure. And the recent pilot that we had in the East Seminole field in West Texas, we monitored it very carefully to make sure we did not exceed the fracture pressure, because we were very close to it. In fact, we designed the surfactant not to be too strong because we did not want to exceed the fracture pressure. And so this is fracture. You don't want to fracture the formation. That's a very important consideration.
And perhaps a bit on a wider scale. So Lucas is asking about the greatest challenges for field scale deployment of foam in various applications, including EOR and CCUS. Do you think it more on the technical side, on the techno-economic side? Where is the bottleneck to have it more to be deployed?
Well, there are two things. One is it's costly because you have to buy surfactant. But the other is that it's very complex. It's as complex as surfactant flooding was. That it's not as simple as most people think, that, oh, foam is just a viscous fluid, we'll just inject it like polymer. You have to generate foam, you have to keep foam stable, and so there's all these other mechanisms that one needs to be aware of. And so if you're not aware of the failure mechanisms, you're likely to discover it whenever you carry it out in the field.
Okay. And there are many comments by colleagues and people who actually were delighted to see you live. And I'm just featuring some of them, like Eric says that it's excellent talk and it's just good to see you. So many have just joined us to just see you and hear from you, which is also good as well. And I have some other technical questions that I will start to proceed with them. Martia Bone is asking, you showed an example in which you had layered vertical, perpendicular to the flow. And we would perhaps also guess that in geology, we may have parallel layer cake type of heterogeneities. In what sense that would be then different than the parallel towards the normal flow?
Yes. Well, first of all, we need to talk about the difference between perpendicular and parallel. The perpendicular heterogeneities is important for foam generation. Now, that's why we did the sandpack experiments. And more recently, Kovacic and the group have done consolidated cores that was laminated. And they show that the laminations provided the heterogeneity for snap-off in the consolidated porous medium. And so that, but yet, whenever you have homogeneous bead pack or sandpack, and possibly some very homogeneous porous medium, the capillary snap-off may be absent if it's homogeneous. That's why the heterogeneity in the perpendicular direction is important for foam generation by capillary snap-off. That's what I want to emphasize.
Bill Rossen,
but now, let me finish there.
Please.
The perpendicular heterogeneity is beneficial for foam generation by snap-off. Now, the parallel heterogeneity, this is what's often the problem with sweep efficiencies in reservoirs. The high permeability intervals in parallel are what we call thief zones. It takes it's a thief. It takes more the lion's share of your injected fluids and doesn't sweep the rest of the reservoir. That's why we need to have mobility control, and that's what I was showing in the example simulation. You saw the high permeability in parallel, but if you had foam, you can generate foam and get it to preferentially go in a high permeability, and then you generate a high pressure gradient, and it diverts the injected fluid into the low permeability. That's how foam can work in a heterogeneous system.
I see. Well, Bill Rossen explains about the capillary end effect as the extreme case for the permeability transition. but also adds to the compliment you gave to him that he says that he should mention that CMG colleagues, computer modeling group in Calgary, they did a lot of contribution in putting this foam models into practice of reservoir simulation as well. So that was kind of a side note, and Bill says hi also from here to you as well. So I have one more global question before closing the session. I have plenty questions here. And that's actually a posting from Ruhi Faraizadeh, who actually sends his warmest regards to you as well. And he's asking about now the role of foam into more energy transition applications. Do you see more of foam we see in the future when we are looking into geothermal, hydrogen storage, CCUS, etc.? Where do you see the role of foam to scale up in the energy transition era?
Currently, what we're looking at is in CO2 storage, but it could be applied to hydrogen storage as well.
Mhm.
That in CO2 storage, that CO2 going into aquifer behaves like CO2 going into the reservoir. That if you have structural traps, that's fine. You don't need to have mobility control. But if you don't have structural traps and you're trying to trap it by capillarity, then the CO2 is less dense than brine. It tends to rise, and then it can go along the top, move up structure, and then migrate to places where you may not wish for it to go.
Mhm.
And so in that case, foam mobility control can give you a greater sweep efficiency, and then that would limit the aerial extent.
Mhm.
But if you have structural trapping, then you may not need mobility control at all. So that when I got started on foam, it was working with steam flooding. And steam flooding, if we can make use of the gravity, then we didn't need to have mobility control. But it was for the flat horizontal reservoirs like the Kern River field, where the dip was so low, there was no way to take advantage of gravity, that we needed to have foam mobility control.
Okay. Thanks very much, George. I see still questions coming. It's 5. We need to, and it's your 11 a.m. after the daylight time saving, etc. All the challenges we had for the test run. It was great to host you. It was our true pleasure and honor, really, to have you here with us this hour. We have an announcement for the next webinar on 20th of April. Sebastian, will you do that, or I go ahead and explain?
Yeah, so the next webinar is on April 20th by Remco from TNO on hydrogen storage. So stay tuned for the title, the announcement, link details, etc. So also from my side, George, thank you for a really nice talk. It was great having you. It's wonderful to have some of the real grandees in our field speaking to us, sharing knowledge that is tremendously diverse, tremendously rich with us and the broader audience, and being able to have that talk archived for generations to come. So it was really our honor to have you. Thank you much, George.
Thank you.
Thanks a lot, everyone. Have a nice week ahead, a weekend, and we see you on 20th of April again. So thanks a lot, George. Enjoy your day.
Bye. I enjoyed it.
Thank you. Bye.
Bye.